This is week 8, so welcome. We will be talking about healthcare profession and careers, the second part of this topic, and then computers and technology within healthcare IT, and EHR. Let's begin with our slideshow.
And the first slide is part 1, Computers and Technology in Healthcare. Let's begin with a general overview of healthcare informatics. This is part 1. Healthcare informatics is the systematic application of information and computer science and technology to public health practice, research, and learning. Healthcare informatics is the specialty that integrates medical nursing science with multiple information and analytical sciences to identify, define, manage, and communicate data, information, and knowledge in healthcare-related practice. Healthcare informatics help healthcare providers, patients, consumers, the interdisciplinary treatment team, and other stakeholders in their decision-making in all roles and settings to achieve desired outcomes. This support is accomplished through the use of information structures, information processes, and information technology. Theories in information science try to explain how we think, store, retrieve, and transmit information. So as you can imagine, healthcare informatics is a field that is focused upon a lot of research in areas such as artificial intelligence, computational neuroscience, cognitive psychology, etc. Part 3. Information is organized data, which means in turn that is a combination of data and meaning. Now, in this analysis of the word, I spell information as in plus form plus action. I want to mention this because the form part means to shape, to create a shape. So to organize data in a perceivable external and internal form, a container, a box that we can, of course, retrieve. Types of data include formatted data, filtered data, organized data, structured, interpreted, and summarized data. This relates to a description, definition, or perspective, more specifically, what, who or whom, direct object, when, and where. Now, since we're talking about healthcare informatics, I just want to digress a little bit to talk about computers. Because, of course, when we think about informatics, we think about how to inform, how to access information, how to share the information, how to relate to the previously understood information, for instance, in the context of reviewing clinical notes, and how to make sure that the accessibility of care is a central piece of our efforts. Now, when we think about computers, we think about computation, we think about calculation, we think about compiling data. So when we think about computer, sure, we could think about the modern development in the field, but it's a really good idea to go back in time and see how, in terms of cognitive processes and the outward representation of this data, humankind was able to achieve that. So on your left side, you see the Lebombo bone, found in the Lebombo Mountains, located between South Africa and Swaziland. And this is something that is connected to our very earliest attempt to encode an organized type of information between 44,000 and 80,000 years BC. On your right side, you see the Ishango bone between 18 and 20,000 BC, found in Ishango in Zaire, or Democratic Republic of the Congo, DRC. So as you can see here, there are certain signs, almost pre-alphabetic signs, lines that appear to be horizontally in parallel to this point, that indicate a sequence that it's a container of a rhythm, a predictive structure, therefore an informational component. In the next slide, a few more examples, more specifically regarding the abacus, that also includes commonality of achievement in history. You can see here the Roman Empire, Phoenicia, and China, as well as the Middle East, Sumer, so Egypt, Mesopotamia, the Persian Empire, as a way to define the earliest beginning of computation from the perspective of creating a catalog of data. Other examples here, the Antikythera computer mechanism within Greece, within the Roman Empire, between 150 and 205 BC, quite remarkable discovery. And more in recent time, we're talking about the 1600 here, in Germany and Giovanni Pollini in Italy, with the earliest version of what we could consider almost a PC, a personal computer. The next slide, also very famous, example by Gottfried von Leibniz in Germany and from Blaise Pascal in France. Finally, one of the essential components in informatics is electricity, you named it. Now, it's really impossible to list all the important years in the history of the development of electricity as a structure, as a method, and a practical scientific application. Just a few names here: Gerolamo Cardano, Luigi Galvani, Alessandro Volta, and of course, especially important because we got the term volt. In England, we have Benjamin Franklin in the United States, we have Hans de Ørsted in Denmark, and Nikola Tesla in Yugoslavia. Of course, many people might remember Tesla and they might think of a car, but of course, in the rest of the world, Nikola Tesla is a fundamental figure in the development of this field. To go back to computers, if we tend to think about the very first computer in the modern sense of the as well as the Berry computer, pretty much at the same time in 1937. In the next slide, we see a few more examples. Let's close this little digression on the history of computers. The Turing machine, one of the most famous ones in England, and then the very first personal computer that was produced by Sebastiano Ziani de Ferrante. That is the ancestor, so to speak, the precursor of all our modern, smaller size computer technology. Now, when we think about information, of course, we don't only think about the machine, we don't only think about computers, but we also think about a net that will allow us to share that information. And when we think about a net in modern times, we think about the internet, the World Wide Web. So let's talk about that for a few slides here. Computer and web-based technology. Important concept: algorithms, data models, natural language processing. And of course, again, as we said earlier, the categories relate to each of the algorithm is a term that in Europe was connected to the Entscheidungsproblem, the problem, the question of decision, of choice. And the term itself, it's derived from the Arab algorithm, which indicates a procedure for accomplishing some task, which given an initial state will terminate in the defined end state. Okay. Now, of course, this is a procedure as in a finite set of well-defined instruction. So when we think about algorithm from a mathematical standpoint, we can think of the application of algorithm in a computer. More specifically, when we think about software. In other words, a computer program is an executable algorithm. Data models. Data models are a concrete representation of an information model. You represent the entities, properties, relationships, and operations, defining the information model in a manner that allows actual instances of those entities to be managed, manipulated, stored, and operated upon and verified. Right? Now, quick thing about data. The term data actually means given. All right. For instance, we in modern English separate data from date, from date in a sense of meeting someone new, as opposed to date as a deadline. Right. That comes from the old Latin data, missiva data, which indicated the fact that someone gave a letter to someone else. It was given. Okay, so that is something that is factual as is given. Okay, and therefore is being received, observed. Natural language processing. Natural language generation systems convert information from computer databases into normal-sounding human language, and natural language understanding systems convert samples of human language into more formal representation that are easier for computer programs to manipulate. Now, we could spend a whole semester talking about this brain-computer interface, the human component of artificial intelligence when encoded from the computational standpoint. But from the perspective of our work here, it's important to understand that the more a computer mimics a naturally occurring process, the better it is at providing that type of fluency that we need to utilize to provide for our patients. Now, I mentioned here, for instance, some categories, especially when we think about clinically speaking, the ICD, international, of course, the DSM, specifically for the United States and specifically for psychiatry. But for the most part, we think of a computer that is able to utilize context, grammar, and syntax in a similar way, at least from a computational standpoint, as a human brain, so that we learn how to put things in categories. For instance, if you think about subject and verb and preposition and so on and so forth, and once we recognize the external box, then we can fill the box with new information because we already have the structure in place. And that, to some extent, at least partially justifies phenomena such as overextension in grammar. If you think about linguistics, when children tend to create a different form, for instance, from a ending verb, the past tense, for instance, or the perfect, then they might create a more regular form in the presence of an irregular verb. Okay, so they might say, instead of I went, they might say I goed, for instance. Okay, G-O-E-D. So they create a more normal, so to speak, version of the verb. So, but that indicates that the child's brain has already possessed the ability to understand what that word means in the context of syntax. Now, of course, by syntax we mean this connection. Again, if you remember the Greek term syn, right? This togetherness, the combination. All right. Now, there is an aspect connected to what we just said. When we think of categories, we think of boxes that we can fill, and this really means that we are better prepared to see what comes next as a new type of information, some elements of which we already recognize. What does that mean? Well, for instance, when we are meeting a new patient, we might be able to assess this person and recognize certain symptoms as part of what we previously learned, as well as what we previously experienced. And so we say, oh, this looks like this type of phenomena. This looks like this type of problem, clinically speaking. And therefore, our judgment will be informed in a way that will actually help us understanding what to expect in terms of the possible issues that medical comorbidities might create in this patient, or actually what to do in terms of helping this patient. Now, when we talk about this type of cognitive lists, cognitive boxes, we also think of taxonomies. So let's see what we mean by that in the context of a theoretical approach to healthcare. This is the next slide. Theoretical applications. By investigating and promoting multidisciplinary interaction resources and implementing the theoretical analysis of medicine, the translational aspects of the field of medical philosophy, notice here it's not philosophy of medicine, it's medical philosophy, help us identify and reduce errors in clinical judgment. This is a brief article that I wanted to quote here. You find the bibliographical references in the module. According to Jean Patel Johnson Shortleaf, a cognitive taxonomy, think of this list in your mind, a taxonomy of errors, meaning clinical medical errors, can A, categorize major types of medical errors along cognitive dimensions. Again, think of this categorization process as what we just said about computers, this series of elements, series of boxes. B, associate each type of medical errors to a specific underlying cognitive mechanism. Okay, so we understand the cognitive portion of what is happening in the moment, and we can extract that aspect and virtually apply it to other areas. C, describe how and explain why a specific error occurs. So as you can see here, we have both mechanism and process, the how and the why. And finally, D, generate intervention strategy for each type of error. Now, this from a psychological standpoint is a much more effective way to categorize this type of errors in comparison to the commonly used brainstorming. Okay, so we have a sequence, we have a category, we have a structure, and the structure creates an informed shape. So we are less likely to continue to produce the same errors, which is extremely fundamental in a field such as healthcare, where from our errors will depend the good or less optimal outcome in our treatment of our patients. Okay. Now, within medical philosophy, I don't want to spend too much time in this context, but think of it as a field that describes the connection between the why and the how of medicine, okay, as opposed to general consideration within philosophy of medicine itself, part of philosophy of science. All right, so in the next slide, we will talk about computers in the context of HIPAA, which we already discussed previously. Based on our previous discussion on HIPAA, healthcare informatics need to satisfy two basic rules: security rule and privacy rule. The first one, need for software and hardware security, access security, and transmission security. Privacy rule, need for de-identified data to provide for patients' privacy of personal information. So we will actually focus on the broader picture here. So we talk about a very brief history of computers, right? And then we just mentioned that we need to think of the net, how we connect this information. How are we going to connect this information? Well, one thing is the theoretical approach. So we talked about categories, we talked about grammar and syntax. We made a few examples like the ICD and the DSM. And we talked about cognitive taxonomies, how to categorize each of these areas. Now, when it's about sharing this data, the net is, in our modern sense of the term, equivalent to the internet. So let's talk about that for just a few slides, right? In this slide, you see the two oldest images, logos, you could say, pictures, relate to the World Wide Web. The first one, the triple W, historical logo designed by Robert Caillot for the World Wide Web, and it was invented, the World Wide Web, by a team led by Tim Berners-Lee at the CERN. It's an acronym, Centro Europeo Ricerca Nucleare. Involves scientists from Belgium, Denmark, France, Germany, Greece, Italy, the Netherlands, Norway, Sweden, Switzerland, the UK, and Yugoslavia. And in the second picture, you actually are looking at the very first picture ever posted on the web. This was 1992. And I also include a link of the CERN.ch for Swiss Federation, Confédération Helvétique, which was the home of the first website. Now, when we think about the internet, of course, we think about a new challenge in comparison to only a few decades ago when we talk about difficulties and possible issues in sharing private information for our patients, personal identifiers, and how to approach that in the most respectful and cognizant way possible. Now, the internet is complex itself, of course, because it is a non-present and yet ever-present dimension. It's a virtual dimension. It's a dimension that it's nowhere and everywhere at the same time. But things get even more complex, more complicated when we think about social media. And that's just a quick reminder here in the next slide. Those two images are the first social media portals in the world, more specifically the United States and the European Union in Belgium. We're talking about 1992, 1997 for a very first example. So you have 6 degrees on top right, and then you have Facebook, which is much more basic in its structure in comparison to modern social media equivalent, aside from the similarity in the name, and the newest version of Facebook that was rebranded, renamed Netlog. Now, needless to say, when we think about social media, we think about a variety of arising issues. So if we're studying healthcare, it's extremely important to understand that whatever is posted on the internet stays there forever. Now, this might be something like a very basic reminder, but whether we're working as a patient sitter, for instance, an LPN, LNA, as a nurse, as a doctor, etc., whatever we share is, in a way, a mirror of how we operate in the system. So just a few basic things to keep in mind. We are certainly not allowed to browse an intranet, an internal digital virtual system, for the purpose of simply understanding and know more about a patient, regardless if this patient is a family member, a close friend of us. We don't have that privilege. We should respect that. We don't even have the ability from an ethical and legal standpoint to venture and see information about patients that are not currently as in the time of our intervention. So for instance, a patient might be discharged from a medical floor and then might be readmitted to a palliative care floor, for instance. So they might switch between medicine, surgery to psychiatry. Now, technically speaking, when a patient is discharged, this person is no longer our patient. So when we think about insurance, it's extremely important as a healthcare provider to know our boundaries from an ethical and legal standpoint. We cannot browse the insurance system of any hospital, clinic, or really any place where we operate. Similarly, we might think of something as quite innocuous, quite positive. We might have had, for instance, a very positive shift at a hospital as a nurse, as a doctor, etc., with a patient who was very, very kind, responded well to therapy, pharmacology intervention, had a lot of positive things to say, and we might feel prone to share the information on social media, simply saying how grateful we are to work in that specific hospital, how happy we are that we were able to work with that patient, and how meaningful our interaction with that person was. Well, while we understand that all the things are positive and encouraging, this does not change the fact that we are sharing possible identifiers on social media. And so we have to refrain from doing any of the above, even if our intent is positive, because we want to protect our patient's safety. All right, let's continue for a few more slides. We're focusing on an analogy here. Okay? We talked about infectious diseases a few weeks ago, and similar to our analysis of chain of infection, disease transmission cycle, healthcare informatics is constructed on plan hierarchies. Okay, so there is a chain, there's a hierarchy, there's a connection. Okay, even a pyramid you could think of. Type: strategic, technical, and operational. Okay, type the type of the plan. Okay. The plan's organizational scope, right? Individual, work group, organizational unit, and enterprise, okay? Finally, plan is in time frame planning structure, immediate, near-term, mid-term, and long-term, traditionally. Now, we had to think of this because healthcare informatics does not work only in the moment. And again, since we talked about the internet previously, and we mentioned that the internet, it's a place that exists nowhere and everywhere, it's outside of physical space. This is also true as far as time. It does not necessarily exist in a specific constructed time. So healthcare informatics have different ways to provide that effort, that insight. Okay, so what type of plan? Okay, whether it's healthcare informatics focus on operational elements, okay, how to achieve that operational goal on a unit, for instance. Whether the focus is on organization as a whole, so how to make sure that every element in the puzzle of the organization works properly, okay? What chain of command we have, for instance, what type of decision-making processes are involved. And of course, we have to think of time, okay? what this plan means in the moment, right here, right now, as well as moving on toward next week, for instance, in the context of discharge planning, which would also in turn involve case management, for instance, as well as long-term thinking about the post-discharge plan, as well as from the perspective of public health policies. Wonderful. More concepts here. Now, when we think about healthcare, we think about different work areas. Okay, there are different focus on each of these work areas. So we can think of healthcare, and we can think of interdisciplinary healthcare informatics. We can think of consumer health informatics, applied healthcare databases, system analysis and design, which is of course a big part of technology, knowledge representation, and interoperability. Extremely important, because if we don't have a flexibility in our healthcare system within informatics, think about EHR, right? Electronic health records. We have to have a system that is internally consistent, that matches its part with the next one, so that we don't find difficulties in accessing information from this portal, from that portal, etc., etc. Okay. Population health informatics. So again, this broader picture, social applicability, accessibility of care, public health, and etc. And finally, clinical decision support. Second part, a few more definitions. We talk about healthcare informatics. So we think of categories, vocabularies, classifications, taxonomies. We already talked about that, and ontologies. So let's start from vocabularies. A vocabulary is a set of words or concepts, right, known to a person or other entity, or that are part of a specific language. Vocabulary, of course, comes from voce, vox, vocis in Latin, synonym for voice, right? Which in turn is connected to the structure of our mouth, right? Os in Latin. And they're the basic building blocks. Classifications. A classification consists of tables of subject headings and classification schedules used to assign a class number to each item being classified, okay? To put it in a class, in a structure, okay? Now, this is already more complex because we have the ability to recognize multiple concepts becoming member of each class, okay? Taxonomies. A hierarchical taxonomy is a tree structure of classification for a given set of objects. It may also apply to relationship schemes other than hierarchies, such as network structures. It becomes more and more prevalent, both at the level of the internet, of course, and virtual shared information, but as well as in the way structures are organized, for instance, in public hospitals. A taxonomy may also be a simple organization of objects into groups, or even an alphabetical list. In current usage, taxonomies are seen as slightly less broad than ontologies. Now, ontologies can be extremely complicated concept, okay? Ontology itself is a compound of being, okay, the onto part, okay, which is connected to the Latin ente, which is also being, a concept of being, the being itself, you could say, and logos, of course, study of being. And I don't want to venture into too profound philosophical consideration here. So let's just see that this very brief description. Ontologies seek to describe the basic categories and relations of being or existence to define entities and types of entities within its framework. So the ontology, the discussion of the existence of something. This is especially important in the context of the existence or lack thereof of a specific pathology, for instance, an infection, okay? Whether its existence is a question of a gradient, okay, or it's a more binary, absence versus non-absence, or lack of absence, or partial lack of absence in the context of a ever-evolving clinical situation. Wonderful. Now, we mentioned very basic things about healthcare informatics, okay? And we talked about basic structures. Now, when we think about healthcare informatics, we also think about what to do with them, because if a person is studying healthcare informatics could be an area to investigate further to find a job, for instance. So let's talk about that for a few more minutes. Job perspective. Beginnings with medical applications of computer science. Medical computer science, medical information science, biomedical computing, medical informatics, healthcare informatics, and clinical informatics are just some elements within the scope of computer science. Okay, so again, beginnings with medical applications. Part two, what to do, what type of job description titles we have. A person who is interested in healthcare informatics might become a business application analyst, chief information officer, nursing information officer, clinical informatics coordinator, director of nursing informatics, director of quality informatics. Faculty, there's a teaching component specializing in informatics. Healthcare informatics software developer, implementation consultant, informatics nurse educator, information system clinical project leaders, information system administrator, information technology training director, and nursing health informatics consultant. So as you can see, aside from linking healthcare informatics to the practice of, let's say, nursing or medicine directly, there are a lot of other fields that a student might be interested in. Now, of course, the key here is to understand both sides of the spectrum, having a solid grasp of the technology you're using in order to create a matching software, to create a program that serves the needs of a hospital, for instance. So you have to be well versed in IT technologies on one side, but also on the other side, understanding the needs, and understanding the needs of a hospital, for instance, also means to understand the jargon, the practical application, how to problem solve a chain of events from the perspective of IT. So it's a quite fascinating field. Few more things in this area, and then we're going to switch gears and talk about other professions, healthcare professions, careers, the part two, because we already mentioned a few things 3 or 4 weeks ago. All right, so healthcare informatics experts formulate models for acquiring, representing, processing, and displaying or transmitting health information or knowledge. Develop computer systems that use the models to deliver information or knowledge. Install information technology system to support such models. And assess outcomes regarding the effect to the overall health system. There's a huge component of health informatics assessment in an almost clinical sense. In the next slide, we have a general overview of medical informatics. Now, I want to stress the importance of telemedicine, especially times we live in, and the fact that telemedicine is produced by technology within healthcare informatics. There's much more health information networks that will also link, for instance, a public hospital with the local or state or federal government. Physician order entry system and direct application, public medicine, policy making, nursing informatics, medical software engineering, medical experts systems, also to link expertise, human and veterinary informatics, computer aided instruction, very, very important, for instance, when teaching CPR to new staff members on a unit, right? And of course, medical software security also connects to what we said previously about HIPAA. Applications part 3, electronic data collection, collaborative tools, geographic information system, data visualization tool, knowledge management system. EHR is probably the queen of all this application, electronic health record, decision support system, registries, electronic lab reporting, electronic disease surveillance, early event detection, especially from a clinical perspective, it's very, very important, and program monitoring and evaluation. A lot of different areas to focus on. Wonderful. We could spend more time about healthcare informatics, but I also feel that we can add more information about that when we discuss this or that part of the product application, because you can necessarily separate the IT component from the clinical intervention we previously mentioned. Now, let's switch gears and talk about healthcare in general, embarking on the second part of now. When we think about healthcare, the two most common professions that come to mind when we think of healthcare are usually doctors and nurses. Okay, now I want to stress the importance of understanding the healthcare professions are mainly subdivided in level, degree, rank, certification, licensure, and scope of practice. This is very, very important, especially for the one of you that might be interested in having experiences outside of your community, outside of your state, even outside of your country. Okay? To understand that there are differences in all of this depending on where you operate. Also to provide yourself with a more insightful knowledge that will also teach you where to start first in terms of your academic education, and also to understand the bureaucratic component of transferring a license, for instance, from one state to another. All right, so the valid degree, rank, certification, licensure, and scope of practice. Granted, in some situations, some of these terms might be equivalent. I'm thinking about certification, licensure, for instance, when a person can be licensed, can be certified, can be rostered, for instance, okay, verified, etc., and of course, level, degree, and rank could also be synonymous, but only in certain situations. All right, now, how to find oneself understanding the complexity of degrees and certifications out there. A good way to familiarize with the process is to understand categories and ranks from the perspective academia. Okay? So what do I need to study to become, let's say, a nurse? What do I need to study to become a surgeon? What do I need to study to become a social worker? A very good place to start is the place where it all started, where it all began, right? And we mentioned previously the oldest university, the oldest continually functioning university is the University of Bologna in Italy, right? So the international framework for academic degrees is still called to this day the Bologna process, from the city of Bologna. Yeah? And that is because that is the structure of academic higher education that was first created, and every other university system follows this system. Yeah? Now, there might be a slight difference in this or that geocultural area in this country or that country based upon linguistic differences or organizational structure of this or that university, but for the most part, these cycles are universally understood in the same way as they are categorized by this Bologna process. You can find out more by going to the main page of the Bologna process on the internet, as well as by browsing the European Union framework titles, especially the European education area. So anyway, the cycles are three. The main cycles are three. Cycle 1, bachelor's degree, or B degrees, from the B of bachelor, for instance, BA, BS, and BSN. Cycle 2, master degrees, or M degrees, for instance, MA, MD, and MS. And finally, cycle 3, doctoral degrees, or D degrees, for instance, PhDs and DSCs. Now, we mentioned this previously. There might be slight different descriptors and titles. For instance, a degree in medicine, the Commonwealth, is referred to as the MBBS, right? Or medicine bachelor, bachelor of surgery. Now, while that technically is a bachelor degree, it's still considered to be, for the most part, a cycle 2 degree. Even though being a bachelor, it might not necessarily require a previous bachelor degree, as it is the case of an MD, which is, aside from the fact of being called a doctorate in medicine, it's not a doctoral degree. So it's not the highest level, it's only cycle 2. And of course, the other thing we mentioned is there is a significant difference between a PhD and DSC, where the first one is Doctor of Philosophy in fields other than philosophy as well, of course, and the DSC is a Doctor of Science. Usually, at least in the United States, those two degrees awarded by American universities are pretty much understood as equivalent, okay? But everywhere else outside of the United States, a DSc is called a higher doctorate. So a doctorate higher than a PhD that is usually awarded to individuals, usually not younger than 40. It's extremely rare to have DSc awarded to younger scientists, and for scientists that have a lot of scientific experience, many peer-reviewed scientific magazines, and depending on which country the DSc is awarded, usually to scientists that have been awarded a previous PhD or multiple PhDs, at least for more than 4 years since their last examination. All right, let's move on. The very last slide is a list of healthcare professions. Now, there are so many that, first of all, this slide is not omnicomprehensive. It doesn't mean that we can discuss every single one of them, or that every single possible healthcare profession will be actually in this list. But it's just an idea on where to start considering possible developments for students that are interested in having healthcare as part of their future career and job applications. So if there's any of these categories that you're interested in and you would like to find out more, feel free to email me and I'll be happy to answer your question in regard to this or that title. So let's just take a quick look, and this will be the last slide for the lecture. These are healthcare professions that are usually divided in categories based on what type of services they provide. So you see the first column in yellow, we're talking about therapeutic services, right? Direct patient care. So if you're interested in working with patients, I would advise you to take a special look at the first column, the yellow. In the second one, you have diagnostic services. Now, of course, all of these services are patient-centered, but this column is mostly interesting for those individuals that might be more prone to be familiar or interested or curious even about technologies, applied science, okay, as well as research. In the third column, the red column, you have health informatics. Okay? Now, health informatics from a broad perspective, sharing information, not necessarily IT. There's definitely a lot of that in this column, but IT is just a minor portion of this. Okay? So you have services that inform and share. Okay? So, for instance, you have ethicists, you have social workers, etc. Support services, essential, extremely important for the perspective of medicine, nursing, and all related professions, because they have to do with what we do with everything else around patient care. Okay? From biomedical clinical engineer all the way to food services, all the way to transport technicians, etc., right? Environmental services, extremely important. Without support services, we healthcare provider will not be able to perform our job. And finally, similar to diagnostic services, but mostly focus on the science part, biotechnology, research, and development. Now, you will see there's a lot of overlap between these two. For instance, you have lab technician on one side, and you have clinical laboratory scientist on the other one. But then, of course, the focus is slightly different, both in terms of what you're actually doing in your everyday 8 to 5 or evening shift work, as well as what type of required academic degree or license or certification you might need. Again, as far as knowing what to study for each of these categories, it's really important to be always up to date, because licensing mechanism and certification vary quite a bit. So for instance, in the context of, say, nursing, there are some country, and within those countries, some states or provinces that will require both a license to practice nursing as a profession, so an RN, a registered nurse, which the registration part is really synonymous in this context, at least, of being a licensed healthcare provider with the title nurse, as well as a at least bachelor level degree. That can be, for instance, a BSN, right? There are other situations where the master level plays more of a role than a doctoral level, only insofar as one is a predictor of the other one. So in certain countries, in Europe, for instance, you cannot get a doctoral degree, for instance, in psychology, unless you have a previous master in the same field, in clinical psychology, for instance. Okay, we already mentioned a few things about an MD type of degree. We also mentioned the fact that there are differences between licensing and registering mechanism. For instance, in the context of psychotherapy and psychology, a person can become a rostered psychotherapist in certain states, for instance, Vermont, and then simply means that the state has to know whether you are indeed practicing psychotherapy for the perspective of clinical intervention and for patient safety, until you will become licensed, which does not necessarily mean that this should be interpreted from a temporal standpoint. A person might decide not to get licensed and keep practicing under someone else's supervision as a rostered psychotherapy. This is legal and very, very common. Or you can become licensed, registered, and then further certified. Okay, there's a lot of certification that can be added. For instance, certification in integrative medicine, holistic medicine, etc., etc. So it's really important to understand that those things vary quite a bit and they keep changing over time. And it's really impossible within a 15-week course to discuss each requirement and each structure for each of these categories and each of these jobs. But again, I'll be happy to answer a question and navigate the complexities of this profession with you if you would like. So thank you very much.
So that was the last slide for this week's slideshow PowerPoint. I will see you all in week 9. So thank you very much and have a good rest of your week.